Hello everyone, welcome to this video on maximum power transfer. So we'll be covering the conditions for maximum power transfer, and we're going to be taking a look at the maximum power transfer equations. So as was discussed in the previous sections, your Thevenin equivalent voltage, your Norton equivalent current are all measures or theorems that can be used to simplify your otherwise complex looking circuit to a simple voltage source in series with a resistor or a simple current source in parallel with the resistor. We went on to further discuss the implication of this type of a circuit, where we said what would then typically happen here is your voltage source, your resistor, and for maximum power transfer, or rather maximum voltage across your load resistor, the load resistor would need to be an open circuit, right? So we knew that the resistance must become infinite such that VTH becomes the maximum value. And similarly here, we picked up that when the load resistor becomes a short circuit, what effectively happens is that the resistance becomes zero such that we have maximum current. So maximum current that's flowing through the short circuit. But we haven't talked about how this is impacting the power that will be absorbed by this resistor. So that's what we're going to be talking about in this particular section. So let's take a look at the voltage source, which we would then define as VTH. We will have our load resistor, which is RTH, and we will have our load, which is RL. What we would now like to know is what needs to happen to the load resistor for us to get maximum power to the load resistor. We knew that the load resistor must be an infinite value for maximum voltage. We knew that the load resistor must be a short circuit, in other words 0 ohms for maximum current. But what about maximum power? Now, for us to be able to determine this, what effectively happens is this load resistor is then made a variable load resistor, and the power is measured across the load resistor as the resistance value is varied from 0 to infinity. Right, so you can imagine that we can put a power meter there, and we start to measure the value of the power as the resistance value RL changes from 0 to infinity. And as we continue to measure this, this is the response that we obtained. Now, given this response, naturally our interest will then be this maximum point, because we are looking for Pmax. So we want to know what is the equivalent value of the load resistor that will result in maximum power transfer to the load resistor, so that we can always make sure that that value is connected to ensure that we have maximum power transferred to the load resistor. And it just so happened that when this was then determined, it was found that this RL value is actually equal to the Thevenin equivalent resistance. And this is why it's so important that we understand and work with the Thevenin equivalent resistance, because what it essentially says is that for you to get maximum power transferred to your load resistor from your circuit, the Thevenin equivalent resistance of your circuit must match the resistance of your load resistor. So for maximum power transfer, RL must equal to RTH, and then secondly, the actual value of your maximum power is going to be given by the following equation: VTH squared over 4 RTH. VTH being your Thevenin equivalent voltage squared over 4 times your Thevenin equivalent resistance. So it's clear that in this equation that for you to determine the maximum power, you need to obtain the Thevenin equivalent voltage as well as the Thevenin equivalent resistance. Thank you for watching this video and enjoy the course.